I don't know, somewhat familiar to you. That's intentional. I want you to start off comfortable. Hopefully it's been a relatively comfortable start. So a limit in which f of x increases or decreases without bound as x gets really close to c is called an infinite limit. And so that's another way of saying that for these types of questions, the answer is either going to be infinity or negative infinity. And if you remember a couple days ago, we talked about how limits might not exist. Remember, there's three ways that a limit doesn't exist. One of which is if you have a different behavior from the left and the right. Yeah? Another one was unbounded behavior, right? And so this is that unbounded behavior. And before we said, hey, we could maybe call these D and E because infinity, as much as we want it to be a real number, it's not a real number. Or we could just describe it for what it's really doing, and we could say infinity or negative infinity. That's where we are right now. So the notation here, again, hopefully this looks really familiar from your summer assignment. Limit as x approaches c of f of x equals infinity. We're not saying the thing that it doesn't mean. We're not saying that the point c comma infinity is on the graph. Right? So if you said f of c equals infinity, we have a major issue because the point c comma infinity can't be on a graph because all the graphs we have are finite, right? And you can't say, and there's infinity. You just can't do it. And so that is not what that notation means. What it does mean is as x gets close to c, y, or f of x, gets huge or small. So it either heads towards positive infinity or heads towards negative infinity. We're just talking about the trend. Remember, might be my last chance to say this for a while, a limit is not really concerned with what is happening when x is c. A limit is concerned with what's happening as you get close to c. Right? What happens around c from the left and or the right. It's not really interested in what is y when x is c. It's a subtle difference, but it's a really important difference when you try to understand what's going on with a limit, as well as these infinite limits. So you're going to find that with these infinite limits, graphs and tables are going to probably be your best tools to be able to see what's going on. And so I've got a couple of examples of graphs here. But before I do, are you guys okay with the notation and how you say it and what it does mean and what it doesn't mean? Any questions there? Anna?
So if it was asking us for a limit and it did increase without bound, you would want us to say that instead of it doesn't exist?
I think it's a better description. Yes. I think saying this versus the limit equals d and e or the limit is d and e, I think saying that right there is a better description. I do. Yeah, so if it were a free response, I'd take either one. If it were a multiple choice, then infinity would, or negative infinity, whatever it happens to be, would be your choice. Any other questions? Okay, awesome. So let's take a look at a couple of graphs here. So when you look at these two graphs, you can see here that you've got vertical asymptotes. In fact, we're going to talk about how when you get an infinite limit.
Would you please send Marguerite Keegan to the front desk with her car keys?
Oh. Yes. Okay, anyways. So we'll find that when a limit as x approaches c heads towards infinity or negative infinity, that's actually a defining characteristic of a vertical asymptote. So if you've got a vertical asymptote, you've got some sort of infinite behavior going on in there somewhere. So there's a definite connection. So if I were to take a look over here on this left graph, and here, kind of, Anna, to come full circle back around to your question a second ago, here's why I think it's best to use the notation we're talking about. So if you look at this one on the left, if I were to say the limit as x approaches 1 of f of x, we're just looking at the one on the left there, graph A, you could say one of two answers. You could say d and e, bless you, or you could say positive infinity, right? Because you can see that as we approach 1 from the left, as we approach 1 from the right, we can see that the y values are increasing without bound. So we're heading towards some non-real number that we have said, hey, that pattern is towards infinity, right? But the one on the right, if we did the same sort of question, limit as x approaches 1 of f of x, this one only has one potential answer, d and e, because not because of an infinite discontinuity, right? Not because of a vertical asymptote. Why would we say D&E for that one? Yeah, radically different behavior, right? It could not possibly be more different. So there's only one answer there. On the left, there's two possible answers. I think that this is a better choice on the left, simply because you're saying, you know what, from the left and the right, we're increasing without bound. If I call both of them D&E, it almost makes it seem like it's the same sort of behavior when it's not. That make sense? Okay. So like I said before, anytime you've got a limit equaling infinity or a limit equaling negative infinity, that's indicative of some kind of a vertical asymptote or some kind of asymptote, vertical or slant, but usually we deal with vertical. And so we're going to talk about how you find vertical asymptotes real quick, and then we'll do a few limits that go along with that. So as a very overgeneralized statement, what could cause a vertical asymptote? As far as like a characteristic of a function. What about the denominator? A zero, yeah, okay, yeah, you're saying all the right stuff, yeah, for sure. So a zero in the denominator could cause a vertical asymptote. There are definitely exceptions to this. So we want to be really careful about saying, hey, anytime there's a zero in the denominator, there's a vertical asymptote, because that's not always true. But this would be kind of our first place to look, first thing to think about. So if you would, take a look at number 1. F of x is equal to 1 over 2 parentheses x plus 1. So please note here that nothing cancels between the numerator and the denominator. And so we will have a vertical asymptote wherever the denominator is 0. So the way you'd handle this is you would just say 2 parentheses x plus 1 equals 0. Fairly easy to solve. End up with x equals negative 1. So if you would, take just a second and graph f of x equals 1 over 2 parentheses x plus 1. Just use your calculator, if you wouldn't mind, and graph that. And then I want to talk about this.
Will we have our calculators on the test?
We're going to talk about that. The short answer is no, not for this first one. But we'll talk about that in a little more detail coming up. And that sort of thing will be true of every quiz and test. There will at least be a section where there's no calculator allowed. This one, the whole thing, no. It's all the numbers, I promise, are quite easy. It's the knowing what to do that you're being assessed on. Okay, so when you look at a graph of this one, can you see that asymptote behavior around negative 1? So maybe you can see, maybe your calculator doesn't show it exactly, but something like this, and then it's like this and this, right? Did I get that right? Okay, so if I said the limit as x approaches negative 1 of f of x, what would you say? Doesn't exist, yeah, for sure. And the reason would be different behavior from left and right. What if I asked you this, though? Limit as x approaches negative 1 from the left. Say again? Negative infinity, yeah. So as you approach from the left, you can see that this graph is decreasing without bound. And then what if we did the limit as x approaches negative 1 from the right? What would that equal? It would be positive. Yeah, because from the right, we can see that the graph is going up, up, up without bound. So what I'm trying to get you to see is the connection between vertical asymptotes and limits that equal infinity and limits that don't exist, and the graph and what the graph looks like as well. So if we can see these multiple representations, I hope that's helpful. Any questions? Okay, so earlier I asked, what can cause a vertical asymptote? We said, hey, maybe a 0 in the denominator. I said that there were exceptions to that, and I want to show you an exception to that, and that is example number 2. And once we do example number 2, I'm going to turn you guys loose and let you just do a few examples on your own. So here is number 2. It says we're supposed to find the vertical asymptotes, same directions, of g of x equals x plus 3 over x squared minus 9. Bless you. So this is a potential trap, not a mean trap. I'm not trying to trick you I'm trying to see if you can understand where a vertical asymptote really comes from. So you could be trapped into saying, oh, 0's in the denominator. So x squared minus 9 equals 0. You factor it, you square root both sides. Whatever method you choose to use, you come up with this, right? And so you say, all right, well, so at plus or minus 3, so two different spots, we're going to have vertical asymptotes. But you know probably that that's not true, is it? There's something else going on. What would I need to do to see what that other thing is that's going on? Factor, yeah, factor that denominator. Make it, you were even doing like the parentheses hand motion. I like it. I think I was understanding you. So g of x is equal to x plus 3. Difference of squares, right? So x plus 3, x minus 3 down there in the denominator. And this is where you see the thing that you need to see, right? So the x plus 3's cancel right on out of there. And anytime you've got a rational function like this and something in the numerator cancels something in the denominator, on the graph, what does that cause? The hole. Or in our terminology in AP Calculus, we call it a removable discontinuity. But it's a hole. Okay, so what that really means then is that when x equals negative 3, we actually don't have a vertical asymptote. We've got a hole. It is a point of discontinuity, no doubt. But x plus 3 canceled with x plus 3. So then g of x, like an equivalent function that's equivalent at every point except for negative 3, really could be represented with that. And so based on that, I think we could now say that there is a vertical asymptote, and that vertical asymptote is where? At x equals 3. That's exactly right. Okay, so this was actually incorrect as far as answering. It just gave one too many. When x is negative 3, we have a hole, and that's not a vertical asymptote. Does that sit okay with you guys? Fantastic. Okay, so I want you guys to make good use of your calculator here, and I think there's a couple of questions left. I want you guys to use a table or a graph. I think a graph in most cases will be easy, so I want you guys to try. Is it 1, 2, 3? 1, 2, 3. It's 3. Yep. Okay, so please try those. 3. Yeah. On what you think here. So for number 1, you might have looked at a graph on your calculator, you might have sketched it on your paper, you might have done a table. I don't know. You had a lot of tools that you could have used. What did you get for number 1 for an answer?
1.
Number 1, you got?
Negative infinity.
Negative infinity. Do you guys agree with that?
Yes.
You guys okay with negative infinity? Okay. You just got the graph in front of you. I trust you that you can read that just fine. How about number 2? 0.5? Yeah. Did this one have an infinite discontinuity? No. It did not. Just 1/2.
Yeah, it was unsatisfying.
Or no, it's like,
It was like
it's a little blip down. Okay.
kind of scary.
Oh, that makes a lot of sense. And so number 3, yeah, like I probably would have preferred that say x approaching 0 because there actually is a vertical asymptote there. You can still look at the graph. We could do both. So when x approaches 3, did you guys get 1/9? Let's look at the graph. Maybe you still have that graph up in front of you because that was the last one. What if it was the limit as x approaches 0 of x minus 2 over x squared? What would you say to that? Number 3. You have that. Get that graph in front of you again. What would you guys say if it was the limit as x approaches 0 instead of 3? Negative infinity. You guys all okay with that?
Yes.
Okay. Any questions at all before we wrap this up? That's it for chapter 1. Okay. So let's do this. This might generate more questions.